Hello, my name is Mykel Kochenderfer. I'm one of the co-directors of the Stanford Center for AI Safety, and we'll be providing an overview of some of the projects we have been working on over the past few months. In our lab, we work on the mathematical models and algorithms for decision-making under uncertainty for safety-critical systems. We're interested in modeling, planning, and verification. Modeling involves going from data, such as aviation radar data, or LiDAR data from an autonomous car, to some kind of probabilistic model. In some cases, there may be inadequate data, and so we sometimes need to incorporate human expert judgment into the construction of our models. These models may range from Bayesian networks to generative adversarial neural networks. Planning involves taking these models to derive a plan. In problems where there is uncertainty, we generally want the plans to be reactive to how the environment evolves and robust to perceptual uncertainty. Validation involves going from this plan to some degree of trust that the system will behave as we intended when deployed in the real world. We'll be highlighting some research that we have done these past few months in these three areas of modeling, planning, and validation. My PhD student, Sydney Katz, will describe this research that we have been working on involving preference-based learning of reward features.
Our primary motivation in this work is to develop a way to model human intent and ultimately to be able to convey that intent to a robot. So in robotics, a typical way to convey intent to a robot is through a reward function. As an example, we can look at this simple grid world, where our intent is for the robot to navigate to the square with the green thumbs up while avoiding the square with the red thumbs down. We can convey this intent to our robot through this simple reward function here. And with this simple specification, the robot will hopefully figure out that we want it to follow a path like this. And this works really well in our simple grid world. But when we move to more complex environments, such as a self-driving car driving down the highway, this can become significantly more difficult. It's not immediately obvious anymore how we would design a reward function to tell our robot exactly what we want it to do in this scenario. And for this reason, engineers have been working on developing tools in order to make this process a little bit easier. One of these tools is preference-based learning. And to learn a reward function this way, we typically present a user with a series of comparison queries, and then we use their responses or preferences in order to encode their intent into a reward function. So in a driving scenario, a pairwise comparison query might look something like what's pictured here, where we ask the user which trajectory they prefer for the orange car to follow. And there's been a lot of previous work that's focused on ways to do this. And most of this previous work focuses on learning a reward function that's linear in a set of trajectory features. So going back to the driving scenario, we might select 4 trajectory features that look something like these 4 features here. And then each of these features for a particular trajectory get multiplied by corresponding weights. We sum them together, and this gives us the final form of our reward function. And typically, the preferences obtained during the learning process are used only to tune the weights in the weighting vector, and these actual features of the reward function are left to be hand designed by the experimenter. And we've noticed in the past when we've tried to do this ourselves, that this actually presents a number of challenges. The first challenge is that this can just be difficult to do. Features are often complex and nonlinear functions, and they can take a really long time to hand tune. Another challenge is that we need to make sure that we're selecting features that are expressive enough to actually encode the intent of the user. And if we don't do this correctly, we've noticed in previous experiments that we might not actually be able to distinguish between the preferences of different users, as shown by the similarity of the optimal trajectories of 15 users shown in the plot on the bottom right. So in this work, we decided to try to come up with a way to ease the burden on the feature designer by allowing user preferences not only to control just the weighting vector in the reward function, but also to influence some of the features. And the way we do this is by augmenting our reward function with an additional feature that's represented by a neural network. And so with this framework, now not only are we able to tune the weights of the reward function, but with sort of a clever choice for the loss function, we can also allow the user's preferences to tune this neural network feature. And so in our final form of the reward function, now our user is influencing both the weighting vector and this feature vector. In order to test the benefit of our method, we performed a study with 15 users on the driving scenario that I showed on the first slide. One metric that we use to evaluate our results is the predictive power. So we can see here that when we evaluate our mixed feature set, including the extra augmented neural network feature, and compare it to the predictive power of only a hand-coded feature set, our predictive power on a test set at predicting which trajectory a user would choose is actually much higher for all 14 of the 15 users. Also, going back to the problem I introduced originally, you see that when we use this mixed feature set, the optimal trajectories among users have a lot more variability. And with this method, we're then taking a step towards being able to distinguish better between individual users' different driving styles. We also wanted to test, though, because we're adding a neural network into our learning process, whether or not we're still going to be able to interpret the results. So one thing we can do is look at the feature value for various different inputs. And this is a plot of what the feature value looks like compared to the hand-coded feature value when we input different headings into our neural network. And we can see that it peaks around a heading of 90 degrees, which would correspond to driving straight down the road. So it's learning kind of some notion of heading. And we also see that when we do this and we look at the feature visualization for different locations on the road, we can see that this particular user likes driving kind of next to the other vehicles on the road, but of course not colliding into them and staying in the lanes next to them. So in conclusion, we trained a neural network that can represent a complex feature that's fine-tuned to user preferences. And this came with a number of benefits. The first benefit is just that it relieves some of the burden of feature design. It's not up to the feature designer to develop all-encompassing features now anymore. And we're also better able to represent user preferences, have better predictive power. And it's a step towards being able to better distinguish driving styles. And of course, even though we used a neural network in this method, our feature was still interpretable.
My PhD student, Chris Lazarus, will describe some research that he has been working on with GE, one of the members of the Center for AI Safety, on runtime safety assurance using reinforcement learning.
As we know, designing controllers for complex settings such as autonomous flight or self-driving cars is a difficult task. Given the potential benefits of autonomy, there is a growing demand to deploy autonomous agents. We are seeing an influx of new approaches to designing controllers. One approach is to use AI and leverage advances in machine learning, such as deep reinforcement learning. Another is to use off-the-shelf open source controllers. The traditional way to ensure safety is to specify safety constraints and encode them in controllers and later verify them and implement them. However, with these new approaches, the controllers can be thought of as black boxes. The problem with black box controllers is that we cannot disentangle their behavior and we do not know the rules under which they operate. For example, it has been shown that deep neural networks are hard to verify. In either case, safety has to be assured if we are to use black box controllers in safety critical applications. We propose to assure safety by bypassing the verification requirement for all the components in a controller using runtime safety assurance. Runtime safety assurance, or RTSA, can be thought of as a safeguard or supervisor that observes the world and given a nominal controller, which in this case would be the black box controller, and it ideally is efficient at performing the mission, but its safety is not guaranteed. And our recovery controller, which is not necessarily great at performing the mission, but can at least lead to a safe stop or reduce kinetic energy. RTSA can decide to take control away from the nominal controller and give it to the recovery controller to prevent unsafe situations. Our approach to designing RTSA is to craft the switch using reinforcement learning. The way to do this is to formally specify what safety means, and we encode that using a safety envelope called E. E is a subset of the state space, and in this example corresponds to a geofence in our experiments. Our experiments were done using a hexacopter in a flight simulator, and E would be the green area in these plots that corresponds to a subset of the airspace. Once we know E, we can craft features to reduce the dimensionality of a problem. As stated earlier, autonomous flight is modeled with many variables, and that makes it a high dimensional problem with complex transition dynamics. Some useful features are, for example, the distance of closest approach to the edge of the geofence, components of the velocity vectors, components of the wind vector, among a few others. Finally, we train our policy using reinforcement learning. And here we have to be very careful because we are indeed trying to safeguard black box components. So we cannot use black box models to do that. This means that we cannot use deep neural networks, and instead we rely on linear value function approximation. That basically means that our policy will learn weights and combine these features to decide whether to let the nominal controller operate or switch to the recovery controller to prevent unsafe operation. Our results, in which we basically compared our RTSA linear value function approximation based policy with a baseline policy, are shown in this plot. Our baseline policy consists of defining a threshold of the distance to the edge of the geofence and deploying the recovery controller when this distance is crossed. The different plot points, the red curve corresponds to different thresholds, and the different points in the green curve, our policy, correspond to different reward functions crafted in a way such that we can tweak the trade-off between safety and efficiency. Of course, we can have a very safe RTSA if we always deploy the recovery controller, but this would make the vehicle really inefficient. On the other hand, we could have a very efficient vehicle, which would very often achieve its mission, but without any safety guarantees. We can observe that our proposed method consistently outperforms the baseline approach and appears to be a viable solution to this problem. Our conclusions are that training RTSA policies using reinforcement learning is viable. This is interesting because we are indeed using machine learning to safeguard the operation of other machine learned components. Additionally, even though we are restricting our models to simple models such as linear value function approximation, we observed that they are suited for this task. And that is great because they're easy to verify, unlike neural networks. And finally, we observed that even in high dimensional complex settings such as autonomous flight, safety can be assured using simple policies learned using reinforcement learning.
My PhD student, Anthony Corso, will describe some of the research we have been working on involving automotive safety validation with adaptive stress testing.
So one of the major problems in autonomous driving is how do we validate the safety of these systems before deploying them on the road? Errors in perception, planning, and control can cause complex failures that may have been difficult to anticipate. So while traditional testing techniques are surely needed, we may also need automated and adversarial testing techniques. But adversarial testing techniques come with their own set of challenges. Number one is that they might find unrealistic scenarios. So consider this situation where a vehicle is driving down the road and encounters a pedestrian that's trying to cross. Our technique, adaptive stress testing, found a failure mode where the pedestrian decides to run headlong into the vehicle, which is coming to a safe stop. So I think we can all agree that this failure mode is probably not first in our list of things that we want to actually solve. The other problem that automated testing suffers from is scalability. So there are a vast number of possible driving scenarios that our autonomous vehicle can encounter. And even in a single class of scenarios, so for example, in this intersection scenario where the ego vehicle in blue is trying to take a left turn, there may be as many as 10 to the 13 different configurations of 5 vehicles on the road. So it's going to be totally intractable to enumerate all of the possible configurations of a given scenario. So to overcome these challenges, we first have to frame our problem as a Markov decision process so that we can solve it with reinforcement learning. So this is really the heart of our technique, adaptive stress testing. We have a simulator that contains within it an environment that the vehicle is going to be driving in, and the environment can contain things like other agents on the road, as well as sensor noise and other perturbations that could affect the behavior of the driving agent. And then we have the system under test, which is the ego vehicle that we're trying to stress test. Outside of the simulator, we have a reinforcement learning algorithm that's able to perturb the environment through an action and observe a reward. Now, we designed this reward function so that the rewards are high when we get situations where the system under test does something unexpected or has some sort of failure. So the reinforcement learning algorithm is trying to find situations that are challenging for the driving agent. So to address the first problem of finding unrealistic scenarios, we can take our reward definition and alter it so that it incorporates something known as responsibility sensitive safety, or RSS. So RSS is basically a set of common sense driving principles, such as don't rear end someone and right of way is given, not taken. And it turns those into formal mathematical statements about which actions are acceptable at a given time step. So what we can do is look at the actions of our system under test and see whether or not they are appropriate according to the RSS rules. If they are not appropriate, then we can be rest assured that something is wrong with the policy that we're running on the system under test, and we'll have found a failure that is actually relevant rather than one that is somewhat contrived, like the example I previously showed. Then the last challenge that we have is scalability. So to address scalability, we've taken the approach of decomposing the scene into a bunch of subproblems that are all in of themselves tractable. So what we can do is pair off each other agent on the road with the ego vehicle and then find failures for that smaller problem. Then we can go back and combine all of these subproblems together and fuse their results in a way that allows us to find failures of the more complex scenario. Okay, so to look at some results, if we apply our RSS metric into the reward function, we now find a very different failure mode in that same scenario that I showed previously. In this case, the adaptive stress testing algorithm finds a mode in which sensor noise tricks the ego vehicle into thinking that the pedestrian is still on the crosswalk or on the sidewalk, but when in fact the pedestrian has entered into the road, causing a collision. So this failure is much more relevant and is something that we'd like to work out before we deploy that vehicle on the road. The next shows results from our scene decomposition approach, where we are able to find failures in this complex 5-car environment using failures found in the 2-vehicle interaction for each of these 4 other agents on the road. And we can actually use this technique to generate a lot of failures and therefore get statistics about how likely it is that our ego vehicle fails. And so this plot shows our estimate of the probability of failure of that ego vehicle versus the number of samples required. And we see that our approach in purple is able to get an accurate estimate of the probability of failure in just about 10 samples, while the other techniques require almost 1,000 samples or don't get a good estimate at all. So with that, I'm going to conclude with 3 points. The first is that we can perform automated testing using adaptive stress testing on automated vehicles to find complex failure modes. But we need to incorporate some common sense driving principles in order to guide the search towards important failures. And lastly, we can use scene decomposition techniques to solve the safety validation problem in complex driving scenarios.
To conclude this presentation, I would like to point you to some additional resources. So the first is a survey of algorithms for black box safety validation. This survey was led by Anthony Corso, and it encompasses many of the emerging research directions. We have also been involved in the building of a number of driver models using generative adversarial imitation learning, and a synthesis of the work that we have done along these lines. We have also done a survey on driver models in general, and we have posted this survey on arXiv. It took about 2 years to write. I'm also really excited about a preprint becoming available of a new book titled Algorithms for Decision Making, where we talk about POMDPs and Markov decision processes, Bayesian networks, as well as validation. If you're interested in receiving a PDF copy when it becomes available, you can register your interest on algorithmsbook.com.